All right, thank you. Can you all hear me okay? The sound and the
Yes.
visuals are good. Okay. I'm leaning very close into my computer because I'm trying to see you. I have a tiny little picture of the room, but I'm watching to see that what your faces are saying and hopefully to hear you because we'll be a little interactive again. Thank you again to the organizers for inviting me to give this lecture series. Um, the the talks all look very cool. And the last talk that I was able to catch a bit of was very exciting. I think I had seen maybe a little bit of this recently in Banff. Um, okay, but let's go ahead and start. We're going to talk a little bit more about the Tamari lattice and its connection to non-crossing partitions today. Let me give you the rundown. Um, so overall, our goal is to sort of give a big picture of some of the lattice theory connections between Tamari lattice and Cambrian lattices and non-crossing partitions. And I know Christian Stump is going to also be talking a bit about this too. I think the perspective will be a bit different though. So yesterday we saw many examples of lattice posets, and I hope I convinced maybe this crowd I don't have to convince, I'm not sure, that lattices are important. We saw an edge labeling of certain lattices which are called semi-distributive, and that edge labeling was by joint irreducible elements. Those are the elements which cover just one thing, and that will come up again today. But we'll actually just talk about some distributive lattices today. So we'll practice using that fundamental theorem of finite distributive lattices. We'll talk about what is a lattice quotient or a lattice congruence, lattice homomorphisms, and then where we will be heading is towards some dynamical stuff, not tomorrow, but on Thursday. Okay, so today in particular, right, we're going to focus on this lattice quotients business, and I'm also going to be telling you about some of the people in this field. And I guess I'll just say this outright, that this is a little bit for, not a little bit, it's for the graduate students in the room, the people who are earlier in their careers. I guess I sort of wish that I had seen more examples. And I mean, I was very lucky to see many examples of people in the field who were relatable to me. And so I want to offer that to you too. Okay. So let's remember what we did last time. We reviewed the definition of a lattice. You were all fantastic in checking which posets were lattices and which were not. We described some techniques for proving whether you have a lattice. And maybe you did your homework and you proved that the weak order is a lattice. Using that BEZ, that sort of local check on meets. And we ended with a connection between the Tamari lattice, which you can realize as a poset on triangulations, or alternatively as a poset on certain permutations, which avoid a pattern. The pattern that we're going to be avoiding is the 3-1-2 pattern here. So this is a bit reiterating some of the things that I've just said, and so I'm going to go past it very quickly and not read these words. We spent some time talking about the weak order, and today we're going to be looking at the connection between the weak order and the Tamari lattice, and then Tamari lattice to non-crossing partitions. So I'll remind you that the weak order you get by looking at one of the ways you can define it is by as this kind of poset of regions where you take a bunch of hyperplanes and they chop up your space, and then you imagine walking away from one region through hyperplanes, and that's taking you up in the poset. We don't have to look at it that way, though. We can alternatively just see our usual Hasse diagram. Let me zoom in since it's very small. And I'll remind you, I believe this is on a slide in a moment, but why not do it while we have the example in front of us? How do I go up by a cover relation? I look for pairs of numbers which are in order, like this 1 and 4, and I swap them out of order. And actually, this is also an example of a joint irreducible permutation, because it has only one way to go down. And if we think about that local definition I just told you, that means that there's exactly one descent, one pair of numbers which are out of order and right next to each other. Okay. So this is me reminding you of that kind of local condition where we swap things out of order. Alternatively, you can collect all of the pairs together of things which are out of order and put them in a set called the inversion set. And now the weak order is just containment of those inversion sets. Okay. And I ended by describing a map which takes my permutations to triangulations. Let's go ahead and do it again, because that was the last thing, and you've had a whole day of lectures and probably had a really nice night out in Vienna. So it's been a while. Let's go ahead and see this map again. So what am I supposed to do? I make this polygon where there's a long edge connecting 0 and n+1, so that n+1 is 4 in this example. I trace out a path along the bottom from 0 to 4. And then I'm going to trace out more paths, one for each number in my permutation. And every time I'm tracing out my path, the next number I see in my permutation, I skip in the path that I trace out. So for example, instead of going 0, 1, 2, 3, 4, I see that 1, and so I skip the 1, go straight to 2, 3, 4. Next, I repeat the process starting at 0, but now I will skip 1. And in addition, I will also skip 3, because that's the next number I see in my permutation. And I go straight to 4. And then finally, I go from 0, and usually I would go 0 to 4, but now I see the 2, and so I skip it and just go right along that top edge from 0 to 4. And in the process, I've traced out a triangulation of my polygon. And I had encouraged you to think about which permutations get mapped to the same triangulation. So maybe in the process, if you were really thinking about it, you would notice that if I did 3, 1, 2, it would also go to the same triangulation. And the key insight is the fact that this kind of number, which is between 3 and 1, is coming later in the permutation. And so we skip it later. And it acts as a kind of hinge between the two diagonals, the one we make when we skip 1 and the one we make when we skip 3. And so in this picture, what we're seeing is these two permutations here both map to the same triangulation. And the observation about this 3, 1, 2, which is pretty clear in our tiny little example, turns out to be true in general. Two permutations map to the same triangulation whenever they're related to each other by a move which swaps. I'm going to say this a bit differently than in the slides. We look for a swap that takes, say, a small number, which is right next to a big number, and then later on in our permutation, we should see a medium number. And so in our swap, this would turn into big, small, and then sometime later, medium. Permutations, which are related by this type of move, map to the same triangulation. And the reason why is because just like in our previous example, this medium number kind of acts as a hinge between the diagonals we make when we skip the small number and then skip the big number. Okay, so this actually helps us understand the whole fiber of this map from permutations to triangulations. I can move in that fiber by doing any kind of swap, which takes a small number, which we're going to use a shorthand and call it 1, and then a big number, which we'll call 3, and swaps them, 3, 1. And the medium number, we'll use a 2 to kind of keep track of that. And that's why I'm writing 1, 3, dash 2, going to 3, 1, dash 2. Okay, so just to make sure we're all following along, it's mid-afternoon for you. Maybe you're a little tired. I've got a permutation here of the numbers 1 through 6. And I'm curious, do you believe that it avoids this 3, 1, 2 pattern? That means that we're looking for a big number right next to a small number, and then sometime later, a medium number. Yes, no? You're gonna have to be loud for me to hear you.
Yes.
Good. I think I agree. So I guess I should look at all of the descents, right? And check. So I've got a descent 4, 2. What are the medium numbers? Well, there's only one and it's 3. It's on the left side. So that's good. And then 6, 5 is a descent, but there's no medium numbers. So yes, that guy is 3, 1, 2, avoiding. That means that I could never find a big next to a small and then a medium. Wish I could swap back into order and kind of move down further in the fiber. So such an element is going to be the smallest thing in a fiber. Because I can't move any further down. We know that moving down in the weak order, right, is this local swapping. I look for things that, I guess if I'm moving down, they're out of order and I swap them back into order. And I hope I've kind of motivated that the only way to move around in this fiber is with this kind of 3, 1, 2 to 1, 3, 2 move. So this would be an example of a smallest element of my fiber because I can't move any further down. Okay. How about this guy? Is this one 3, 1, 2 avoiding?
No.
Can you tell me an example that shows you?
2, 5.
Yeah, at the end. That's good. Okay, those guys all happen to be right next to each other, but they don't have to be. That medium number can be further away. Just out of curiosity, is it 1, 3, 2 avoiding? That means, can you find a small thing next to a big thing and then the medium number somewhere later?
No. It's
4, 6, 5.
also 1, 3, 2.
Yes, good, good, good. So this one, right? Yeah, you found many examples, but I definitely heard somebody say the 4, 6, and then the 5 is a little bit later. Yeah, that would be an example of this 1, 3, 2. So this permutation is neither the smallest nor the biggest in its fiber under that map, which I think I used eta to denote. Excellent. Okay, so I want to talk to you about these types of maps which preserve lattice structure. And I'm not going to prove to you that this map is a lattice morphism. It happens to be, but I want to kind of give you some of the tools that you would use to check it. And actually, our discussion right now got us pretty close to everything we would need to check. There's one more detail, and I'll point it out to you when we get there. All right, so what does it mean to talk about a lattice morphism? What are some conditions that we would want to check to see if we have a map between posets? When is it going to be a lattice, a map really between lattices? Okay, it's exactly like in any kind of algebra setting. It needs to preserve the operation. So our map should preserve joins and should preserve meets. Great. Let's look at some small examples and see if we can use this definition right here to check whether our proposed map between two things which are small enough that it's very clear they're both lattices. let's look at some examples and see if we can check whether we have an actual lattice homomorphism. Oh, bless you.
It's working.
All right, take a moment, think about it. Remember your map, which I guess I called phi here. It should preserve joins. So for example, if I've got an X and a Y, and I take their join on the left side, and then look at the image and take the join there, which, you know, are going to be kind of different, I should still get equality. What do you think?
No.
No. Okay. And how do you see it? Can you tell me what elements to pay attention to?
C and D.
Yeah, that's great. C and D. Excellent. Also, I can hear, there's at least one person I can hear very well, and I appreciate that. If we take C and D to be like our X and Y, okay. What is the join of C and D? It's very obvious. Let me hear you say it.
The join of C and D is 1.
Excellent. Great. And so that should be Y. However, the of Y. Okay. No, I wrote the right thing. Great. However, if I do first the map and then the join, they both are going to X in my picture. That's what the yellow is supposed to tell you. And so I'm taking the join of X with itself, which is X. So those are not equal. Great. So there's something wrong if our fibers are not intervals. It's part of what we're seeing here. Here we have a yellow fiber, which is closed under going down, but has 2 maximal elements. And that caused some issues. This one is slightly more subtle. What do you think? Is it a lattice map? The colors are telling you the fibers.
Oh.
No, excellent. You're right. It is not a lattice map. I'm gonna talk through it because maybe it is difficult to see, but you can look at the A and B here. Okay, so I called this guy psi. Psi of A join B is the top element. So that would be U on the right side. But now if I do psi of A and psi of B individually, I get S join R, and you maybe recall from last time that when you take the join of comparable elements, you just get the bigger thing. These are not equal. So here we're seeing something a little bit different because all the fibers are intervals. But the issue is there's an order relation between fibers. There's sort of an order relation which is not being respected, is maybe a way to say it. The fact that at the bottom here, it seems that the yellow fiber should be bigger than the blue fiber is not preserved as I go up, because now I have incomparable A and B, and that was kind of how we broke this example, actually, is using the A and B to get a join, which kind of messed up everything else. And so there's sort of an order preserving property that we need to keep as we look at these fibers. Okay. This one, I'm going to ruin it for you and tell you, yes, this map is a lattice map. So it does preserve joins and meets. And we see, first of all, that our fibers are intervals. And secondly, the fibers somehow are respecting the order relation. And we do have some elements which are not comparable in the fibers. However, the smallest elements are ordered as they are on the right. and the biggest elements are ordered as they are on the right. And that sort of saves us. So I could check if I do a row of A join row of B, I do get X join Y, which is Y. Row of A join B here is row of the top element, which is also Y. So even when I look at the pair of incomparable elements and try to break it the same way we did before, it's okay. Okay, so to summarize what we were observing, our fibers must be intervals when we look at a map between lattices. The bottom of the element of the fiber needs to be order preserving. If I map the bottom element to its image in of the whatever my lattice map is, and similarly the top elements. So you might notice that a lot of the discussion is centering really on properties of the fibers and less on properties of the two lattices. And so this suggests maybe instead of thinking about the map itself, it's helpful to just think about an equivalence relation on the domain lattice. And that is indeed what we will do. So an equivalence relation which respects the join and meet properties. And so will always give us, will sort of correspond to the fibers of any lattice map. It's called a lattice congruence. I just hinted at this, that every lattice morphism gives us a lattice congruence via fibers. And every lattice congruence can give us a morphism via a quotient construction, similar to what you see in all sorts of algebra settings. So if we now take as our L prime the equivalence classes of this equivalence relation, and the join is just the join of representatives and the meet is the meet of representatives, then we get a new lattice, and then there's a kind of obvious map from L onto this quotient. Okay. So I think I didn't say this very well the first time, but what we were just seeing is that we can check whether an equivalence relation is really coming from a lattice congruence or a lattice morphism if the following three properties hold. First of all, our equivalence classes need to be intervals. And we saw that that was important in our first example. Secondly, if you map from L, an element in L, to the smallest thing in its class, this map should be order preserving. And similarly, the map to the biggest thing in its class, since our classes are intervals, that should also be order preserving. And we saw that that was important in the second example, that when that gets broken, somehow we're not going to either preserve joins or meets. Okay, so the map from the permutations to triangulations that we were studying earlier is a lattice map. I haven't really told you that the Tamari lattice is actually a lattice, though, and this map can induce that lattice structure. So what this theorem is actually saying is that the fibers of the map are a lattice congruence. And so the Tamari lattice can be obtained as a quotient lattice of the weak order, which we did describe. We did sort of sketch out the proof of why that guy is a lattice. So what if we checked for this lattice congruence property? We already know that our fibers are intervals because I told you how to move around in the fiber. using these 1,3-2 to 3,1-2 moves. What you still have to check is that projecting down to the smallest element in the fiber is order preserving. And the dual of this guy. But that's not hard using inversions. So I'll leave that to you as an exercise. Remember, we also kind of know what these smallest elements are. They're the elements which avoid the 3-1-2 pattern. So here's an example on S4 of the fibers of our map from triangulations, sorry, from permutations to triangulations. And now I want to zoom out a little bit away from Tamari lattice land and think about actually all of the congruences that we could make from the weak order, for example. So we know that our lattice congruences, as in the previous example, form a partition of our poset, right, into fibers. Those are our equivalence classes. And so we could take all possible partitions of this lattice and order them by refinement. And hey, we know what that's like a partition lattice, right? It turns out that if we just focus on lattice congruences, this is a distributive lattice. And we like distributive lattices because we have a fundamental theorem of finite distributive lattices, which says our lattice must look like a poset of order ideals for some poset. So what could this poset be if we happen to be focusing on the weak order? Okay, answering this question, I think is interesting on its own, but it's also going to highlight some things about the Tamari lattice and how we construct the Tamari lattice. Okay, so we know that all of our lattice congruences are coming from these fibers. You can actually think of the fibers obtaining our quotient by contracting down those fibers to the bottom element or the top element. Either one is fine. And when we think about it that way, the edges of the poset become important. And we also know that the weak order, those edges are labeled by joint irreducible elements. So it turns out that each quotient, okay, this is important, so I'm going to actually highlight it as I read it. Each quotient of the weak order is determined by the collection of edges, which we contract, and in particular, which edges are joint irreducible edges, or what labels are we contracting? So this poset P for our lattice of congruences is actually a poset on the joint irreducible elements of the weak order. Now, there's something confusing about this statement. I am not saying that the lattice of congruences is the order ideals of joint irreducible elements ordered as in the weak order. The poset here, the elements are joint irreducible elements, but the order relation is different from the weak order. So we need to understand what that order relation is. And actually, maybe we want to understand our joint irreducible elements a little bit better. Right now, we know that they're determined by a descent, but there's a little bit more information. Okay, so our goal is to describe this poset of joint irreducible elements, which is not just a subposet of the weak order. And so we're going to really make sure we understand these joint irreducible elements. We know that every joint irreducible has a unique descent. So we're going to pick a pair of numbers A and B. That will be our descent. And then there's one other piece of information that came up in our labeling yesterday, which is that I look at the numbers between A and B. So these are like, I don't know, middle numbers between A and B. And we know in our joint irreducible element, they will be on either one side or the other of the descent. And so that one side or the other is the last piece of data we need to keep track of to determine a joint irreducible element. And actually, I only need to know which ones are on the right side because everybody else will be on the left, right? And so this set R, you can think of as right. These are the points which are on the right side of my descent. So we encode all of this data in a picture. What we do is we take a bunch of dots, we put them in a vertical line, we pick out our A and B, that will be my descent, and then to keep track of the points which are on the right, I'm going to draw a little arc, and points which are on the right side of the arc are in my element, are in my set R. And since it's a descent, we kind of imagine that like we're a little car traveling down this arc. Okay, so here's what these arcs look like for S4. These are all of my joint irreducible elements for S4. There should be 11 of them. So for the grad students in the room, you count the number of joint irreducible permutations. All right, so the description of this poset, which tells us about all lattice congruences, is quite nice in terms of arcs. So Nathan Reading in 2015 proved that the poset we need on our joint irreducible elements, which we're just going to call them arcs now, for now on, our poset on arcs is one arc is smaller than another one, if and only if I'm always going to say this backwards, so I'll actually read the slide to make sure I say this in the correct order. Alpha, arc alpha is less than beta, if and only if beta is a subarc of alpha. So what is a subarc? Let me show you with a picture. We'll see the whole, we'll see both the lattice of all possible congruences on the weak order for S3, where what you're seeing are the fibers, right? You're seeing those equivalence classes. So at the bottom, everybody's in their own class, and at the top, everybody's together. We saw these co-atom congruences here as one of the example congruence maps. So I highlighted for you, I drew a little picture next to some of these lattice congruences. This one, this one, this one, and this one. Those are the joint irreducible elements in this lattice of congruences. And so the P here is exactly that poset of joint irreducible congruences. And in terms of arcs, what we see is the bigger arc is a subarc of the smaller thing, which I have not defined. The way to make a subarc is you pick some endpoints between the endpoints of your given arc. So maybe I would pick 2 and 1, and you slice horizontally. Oh. And take whatever, imagine reattaching wherever you've sliced off your arc at the bigger endpoint. And that would give you a subarc. Let's see a bigger example. Here I wanted to show you the whole lattice of congruences. Let's just look at this poset of arcs. So here is the poset of arcs for S4 And remember, as you're moving up, you're seeing smaller subarcs. So combinatorially, a subarc should sort of have the same left-right data as the bigger arc it came from. And here, if I wanted to do that slicing that I saw before, I could slice off this bigger arc corresponding to the joint irreducible element 2, 3, 4, 1. And the subarc I would get is right here. Okay, so let's see this in action. What I'm saying is that if I take any order ideal of this poset, that should give me a lattice congruence, and from that lattice congruence, I get a lattice quotient of the weak order. Here's one such order ideal. I am now going to look at my weak order and contract any label of a joint irreducible, any edge, which is labeled by a joint irreducible in that order ideal. And this is exactly the congruence that gives me the Tamari lattice. But I can do any kind of order ideal that I want. So here's another one. Here's the corresponding congruence. And here I've contracted those yellow edges down to their smallest element of the fiber. So why am I talking about lattice quotients? Why not just prove the lattice property directly on the Tamari lattice? So the nice thing about viewing the Tamari lattice as a lattice quotient of the weak order is that it inherits the nice properties of the weak order. So last time we talked about the fact that the weak order is semi-distributive, and now we automatically get that property for the Tamari lattice. We talked about how the edges of the weak order can be labeled by joint irreducible elements. And so now the Tamari lattice gets an edge labeling too. And we now know that joint irreducible elements are kind of nicely encoded by these arcs. And so we can label the edges of the Tamari lattice by arcs. And actually, they're the arcs that are not part of this order ideal from our lattice congruence. So I'm going to call those the uncontracted arcs.
Can I ask a question?
Sure.
Yes, can I bring the,
I can hear you pretty well, Cesar.
So this is very special for the weak order. So the
And in type A also.
lattice quotients, a distributive lattice, taking the partitions they determine. But let's assume I have another lattice.
I think in general, lattice congruences always form a distributive lattice.
That's
And
true.
what is a little extra special here is that the poset, which determines that distributive lattice, is actually a poset on the joint irreducible elements. So that may not be true in general.
I see.
Okay. Oh, I'm watching the time. How long do I have? Am I already over?
10 minutes. Or
I have 10 more minutes. Okay, great. Thank you. All right. So the upshot of this is that we can label the edges of the Tamari lattice by joint irreducible elements, which we think of as arcs. And here I did that. And as you can see, the picture is very small. It's kind of hard to see, but I've labeled every edge here by the corresponding joint irreducible element from the weak order that was giving me this kind of semi-distributive property. We had talked about this last time. up here, you'll notice that none of my arcs go to the left side. All of them are to the right side. That's actually somehow equivalent to that 3-1-2 avoiding. Now, I think this picture is a little hard to read because the arcs are so small. So instead, what I'm going to do, and I'll zoom in at this 3-2-4-1, is I'm going to take the arcs that I see below a given element, and I'm just going to put them together in one picture. Okay, so what that would look like is this. Instead of seeing the two labels on my edges from that semi-distributive property, I'm going to just put those arcs together in one picture. I'm going to do that for all of these elements. And now that's much easier to read. And this has the nice property that when we put these arcs together, they do not cross. They can share endpoints. The only way they share endpoints, however, is if we imagine traveling on our arcs, that shared endpoint has to be the target of one arc and the source of another. So what is extra nice and why I wanted to share this with you is that this arc diagram picture of the elements of our Tamari lattice also make it easy for us to see the correspondence to non-crossing partitions. So what I can do is take a circle, add vertices along the boundary of that circle, and you'll notice that none of my arcs are allowed to go to the left. And so what I'm going to do is I'm going to follow that in this edge labeling, or sorry, in this labeling of my vertices to force the arcs inside of my non-crossing partition to kind of do the same thing as the arcs in this non-crossing arc diagram. I put all of the vertices from 0 to 8 kind of on the left side to force my arcs to go towards the right. And all I do is I trace out my arc, for example, the arc that goes 8, 4, 3, 1. I trace out that exact pattern here, and then I close it off. I sort of take the convex hull. And I do this for each connected component of my non-crossing arc diagram. And this is a bijection from the Tamari lattice to the non-crossing partitions. Okay, so I haven't featured any lattice theorists today, but I wanted to feature somebody that I've been working with for the last couple of years, Ashley Tharp, who has been working very closely with these non-crossing arc diagrams. And we just heard a talk about the core label order. So Ashley was studying the core label order or shard intersection order of types A and B, and looking at actually like a lattice maps between those. And so it's really helpful for her to have kind of good understanding of those orders in terms of these joint irreducible elements or these arcs. And so with Ashley, Nathan and I have extended this theorem, which is really what we've been talking about for most of the talk. It's saying that the congruences of the weak order are determined by arcs. This is a slightly more precise statement. This says a collection of arcs are uncontracted by a lattice quotient if and only if that collection of arcs happens to be closed under this subarc relation. So with Ashley, we have extended that to type B. And so we have a notion of what arcs ought to look like there. And Pedrol and Pilo have also a similar notion of arcs in type B. And then we have also extended this to type D. And so I want to end today's talk by showing you some pictures of what these look like. So
Only if I can, I wouldn't interrupt, except there's a student, also Ritter with Pedrol and Pilo. Ritter was the student there, so I wanted to make sure that we didn't leave.
Oh, thank you, yeah. Sorry, Ritter. make it highlighted. So here are our non-crossing arc diagrams in type B. The X is because we have taken, actually similar to type B non-crossing partitions, these arc diagrams satisfy a central symmetry. And so we quotient out by that central symmetry. And that's the picture that you're looking at here. So you're sort of seeing half of an arc diagram. Or if you're familiar with type B permutations, you know that you can determine the permutation by its window notation. You only need half of it because of the kind of symmetry that determines a type B permutation. So you can think of this as like a window notation for our non-crossing arc diagrams. So as in type A, we have a nice map from these non-crossing arc diagrams in type B to non-crossing partitions. And it's similar to what we were seeing in type A, actually kind of the same construction, except it's, we've quotiented out by a central symmetry, and you can see there's kind of orbifold point down here in our non-crossing partition. And I guess Nathan is going to talk about non-crossing partitions on surfaces, so maybe you'll see more of this. And here you're seeing all of the non-crossing arc diagrams in, I guess this is in D3. And these are very interesting. So they break some of the rules we were used to from type A. So I think that I'll end there. Thank you all for listening.